Well, thank you, Brian, and thank you, Terry. I'm going to start out by just quickly going over what I'm going to talk about. So I'm hoping that these slides are going to advance not too slowly, but the benefits that I'm going to describe are based on, as Brian says, the first 20 years, or the last 20 years, which is also the first 20 years of the FGrOW RLP project. And I will be, for the most part, I'll spare you the detail of the design and statistical analysis and focus on the demonstrated effects of reforestation treatments. I will, however, start with a quick summary of the information sources on which these results are based, and I'll end with some design recommendations that you might consider for continuation of the study. The RLP trial, which served as the main source of information, was established in the year 2000, and as somewhat illustrated on the slide, it has a well-replicated controlled split plot design to investigate the effects of planting density, weeding, and pre-commercial thinning on post-harvest stand development of lodgepole pine in the Alberta foothills. Development has so far been tracked through what amounts to the entire regeneration phase of the rotation. This allowed us to develop FGrOW, which I talked about at my last webinar. It's a regeneration model linked to the government's growth and yield projection system. I'm also going to briefly mention related work, some supported analyses that we did of the RLP trial, some of which have been published. The Sundance site preparation trial, which looked at both site preparation and harvesting effects, and work that Sharon Meredith and I have done on stand development following MPB attack. But most of what I'm going to present today will be forecasts and projections from FGrOW. And specifically, regeneration performance forecasts to stand age 18, which is how we've been marking the end of the regeneration phase, and onward projections by Gypsy to rotation age. And I'm going to be discussing effects for mechanical site preparation, planting, chemical weeding, and pre-commercial thinning. Pre-commercial thinning including manual brushing of hardwoods. And as I mentioned, I'll talk about regeneration performance 18 years after cut, and then pine merchantable mean annual increment projected onwards to culmination age. A couple of points I wanted to make by way of a preamble, though, is that discussion of the benefits of these treatments are pretty much meaningless unless we qualify them by site. And for example, what I mean by that is each of the 4 treatments that I'm going to be talking about, we have found or demonstrated to be essential on some sites, but or at least be arguably essential for meeting forest management objectives on some sites, and having no benefit on others. So it's for that reason that I'm going to try to illustrate treatment responses across some ranges of site conditions, and you're going to hear me talking about sites with high modal and low potential for mortality of planted stock, for natural regeneration of pine, ingress of natural regeneration of pine, hardwood competition, and growth. I have this table looks a bit onerous, and I'm not expecting you to remember it for the rest of the presentation. But what I've tried to do is identify here scenarios for illustrating responses to treatments and how these are influenced by different site conditions, specifically using the same site variables that are recognized as input by FGrOW. These are listed in red across the top of the table. I have identified modal conditions based on the RLP trial. That's in the first line, the first horizontal, the first row there shows those modal conditions based on the RLP trial, the most commonly occurring conditions across our system of sample plots. And I hasten to point out that those modal conditions may not be your modal conditions in terms of what you're interested in for your particular timber supply area, forest management area, or whatever. But I've done that as a basis for comparison with sites which have relatively high and relatively low potentials for affecting, on the one hand, mortality of planted stock, on the other, ingress of pine natural regeneration, growth of pine, and hardwood competition. And I've identified for each of these responses, you'll notice that the 4 site variables most that I find most influence the response, and those are indicated by the crosses in the horizontal rows. And so just to get, well, I'll quickly go through these to make sure you've got or try and make sure that you've got the idea. So what we're saying is that, for example, site potential for the mortality of planting stock is worst on the drier but more organic soils in the southern lower foothills, and is less on moist but mineral soils as you go north and up into the upper foothills. Ingress, that's ingress specifically of lodgepole pine. The potential for ingress is best on medium nutrient mineral soils, more so at southerly latitudes than northern, but is also, of course, dependent on ground cone densities present at establishment. And growth, by which I'm primarily referring to top height age, the top height age trajectory of pine, is potentially greatest on rich mesic soils at low elevation, and much less on poor, moist, high elevation soils on steeper slopes. And then finally, I'll be talking about hardwood competition potential, which is greatest on rich, low elevation soils particularly in the southern lower foothills, and least on poorer soils at higher elevations and latitudes. So here we go. I'll start out by talking about the effects or benefits of mechanical site preparation. I have tried in this and the following slides to be somewhat consistent in showing, first of all, at the top, a title indicating the treatment and the attribute of interest. And there's a yellow footnote at the bottom of the page, giving more detail on the specific scenario that I used. In the 3D bar charts, site potential, in this case, mortality potential, high, modal, and low, is shown in the left floor axis, and the treatment, drag, mound, or none, is shown in the right floor axis. And the response, which in this case is density of pine, trees per hectare, at 18 years, is on the vertical axis. And then there's a statement below the bar chart, which is where I'm trying to basically come up with a conclusion. So in the case of survival of planted stock, mechanical site preparation, whether it's drag or mounding, and in this respect, we didn't find a difference between the two, improves survival, particularly on sites with high mortality potential. And that is demonstrated by the projected density of planted trees 18 years down the road, actually 17 years after planting, planted at a density of 2,000 stems per hectare. I'll come back and summarize for mechanical site preparation as a whole once I've been through a few more of these scenarios. So here we're talking about the effect of mechanical site preparation on projected MAI of planted stock. This is mean annual increment of pine projected to culmination age, and this is considering just planted stock and ignoring natural regeneration. And you'll see here that the mechanical site preparation, and this is as a result of the mortality, the previous survival / mortality that I talked about, that increases MAI on sites, or is projected to increase MAI on sites with high mortality. There's also quite a bit of variation, you'll notice, between across our range of sites, from high mortality potential to low mortality potential. And let's move on then to, well, just to be clear, what I'm saying is that, oh no, sorry. I know what I wanted to mention, and this applies to subsequent slides as well. And when I talk about mean annual increment, I'm talking about merchantable mean annual increment at the age of culminations. But please note that these projections do not take into account differences between experimental and operational conditions. So, and I talked about this in the last webinar on FGrOW, or the last webinar that I gave on FGrOW, and this can reduce MAI projections by anywhere from 25 to 35% relative to what I'm showing here, which is based on the model, which in turn is based on the experimental data. So let's press on with some more mechanical site preparations effects. Drag scarification is beneficial on sites with low ingress potential. It can be beneficial on modal sites where stocking may be marginal. For example, on our modal site conditions in the RLP trial, a lot of those sites would, support natural regeneration at right around 80%. And so if you wanted to be sure of getting that over the 80% mark, then mounding wouldn't make much difference, but dragging wood. Having said that, mechanical site preparation, none of the methods have very much impact on sites with high ingress potential. Because in this part of the world, where you have high ingress potential, you tend to get very high levels of stocking anyway. Density of pine ingress. So this is has some similarities to what I said about stocking, but some important extra attributes. Drag scarification, as you all know, increases density of natural regeneration of pine. Whereas we might want this, especially on sites with modal or low ingress potential, very high densities are likely on drag sites with high ingress potential. If you combine dragging with sites of high ingress potential, you can get these extremely high densities as you tend to get in fire origin stands. And how does that all play out in terms of projected mean annual increment of ingress? Again, in this case, we're talking about just ingress and assuming no planting. Notice that if you look at the high ingress potential combined with dragging, that very high density shown in the last slide has resulted in density-induced regression. And as you see in the sort of the back left-hand corner of the histogram, where the MAI is considerably lower than under the mounding or no treatment options. And conversely, we can expect little or no mean annual increment of pine on non-scarified sites with low ingress potential. That's based on natural regeneration. Obviously, on those plants you would be looking at, on those sites you would be looking at planting. Okay, I just want to, as an aside, talk briefly about harvesting effects. We did not attempt to model the effects of harvesting methods in FGrOW, but the Sundance site preparation trial that I mentioned allowed evaluation of the effect of slash retention versus slash removal. This was designed to emulate stump side versus roadside logging. And you'll notice in the left bar chart that both mechanical site preparation and specifically dragging and there's no significant difference between dragging and mounding, or not very little, but considerable difference between MSP and no MSP, and none. And and also the harvesting method affects mortality, which is higher with slash retention than without. And we'll talk about what that might imply a little bit further on. On the right-hand diagram, this is an evaluation that we made in lower foothill stands 10 years after MPB attack. And I really just wanted to include it because it serves to demonstrate the lack of pine regeneration you get when there is no soil disturbance. And this obviously is not relevant to normal practice, normal reforestation practice, but it is relevant to the situation we can find ourselves in with Mountain Pine Beetle. And under these circumstances, if you are unable to salvage and do site and do harvesting and other ground disturbance, then what we found in the plots that we looked at was that natural restoration is totally dependent on the incident of non-pine regeneration and advanced growth. But okay, back to the main topic, and summing up for a mechanical site preparation. Mechanical site preparation improves survival and mean annual increment. One in particular of the studies that I did, and some of the other work we did with the CFS, would suggest that this improved survival is related to better root health, and for example, we found less armillaria after mechanical site preparation, and also less hylobius damage. Obviously, drag scarification increases ingress density and stocking. The slash removal that I alluded to reduces mortality, as I mentioned, but also in the study that we did with Simon Landhauser, that does appear to increase growth relative to a slash retention. But that leaves a bunch of risks and uncertainty. Again, stating the obvious, pine is unlikely to regenerate satisfactorily in the absence of soil disturbance, which is obviously a risk when we're confronted with non-salvageable mountain pine beetle attack. But again, back in talking about normal reforestation, dragging, as many of you will have experienced, can cause excessively high density and reduced MAI on sites with high ingress potential. I should just briefly mention that we did have some mechanical site preparation data in the Lodgepole Pine trial, but it was not experimentally controlled. The only trial where we had experimentally controlled data for site preparation was in the Sundance trial, and the limitation with that is that that was confined to relatively poor sites in the upper foothills. Okay, so now I'm going to talk about planting and showing on the planted trees per hectare on the right-hand side and ingress potential on the left-hand axis. So planting improves stocking on sites with low ingress potential and reduces risk of unsatisfactory stocking on marginal sites, and has, as mentioned in the case of mechanical site preparation, little effect on stocking under high ingress potential. So not too many surprises there, I think. How does that translate into basal area? This is basal area at the end of the regeneration phase. So planting increases basal area at the end of by the end of the regeneration phase, and in no uncertain terms. And that translates, or this shows how it translates into projected mean annual increment. Planting certainly increases mean annual increment, but the increase that you see with planting density is not linear. It tends to level off, which you might expect as you go to higher densities, and it does vary across sites. So just to summarize, talking about planting effects, planting benefits, improved stocking, because it improves site occupancy, especially on sites with low ingress potential, but it also increases projected MAI. I don't think any of this is too surprising to you. It may not always be cost effective, for example, on modal sites with high ingress potential. But of course, I appreciate that many silviculturalists have to weigh up the risks of not getting that right and plant as a risk. If you're risk averse, you plant to make sure that that you don't have regeneration failures. But one point I would stress is that poor health and survival on sites with high mortality potential do represent a considerable risk. They represent a considerable loss of planting stock, and of course that's even more important if you're talking about improved stock and so on. Let's get into chemical weeding. Let's see. Percent stocking of aspen. Chemical weeding has little impact on sites with low, or in the case of the RLP modal conditions, has little effect on modal competition, on sites with modal competition potential. But chemical weeding is extremely effective on competitive sites, at least under experimental conditions. And as I mentioned in the last webinar, it does represent an uncertainty because we don't necessarily see this level of effectiveness in operational data, or at least it appears we may not be seeing this level of effectiveness based on what we can deduce from operational data like the RSA data in the empirical post-harvest database. Weeding is essential. If we look at the percent stocking of pine, as distinct from that of aspen, weeding is essential to maintain pine stocking on competitive sites. Chemical weeding is essential to maintain stocking on competitive sites, but again, has little significance elsewhere. And similarly, if we project now pine MAI, weeding is essential to maintain pine growth and yield on competitive sites, but has a little effect elsewhere again. So what can we say about chemical weeding? Major improvements in stocking and competitive and projected yields on competitive sites. And on the more competitive sites, that makes the difference between success and complete failure of meeting a coniferous management objective. But there are a number of risks and uncertainties. Disparities between experimental and operational data. One of the risks that you guys I know are always having to contend with is the risk of failing to recognize sites requiring, I'm sorry, I didn't mean to advance the slide, requiring or not requiring treatment. There's obviously costs associated with both misidentifying sites that don't require treatment and misidentifying those that do. One thing I should mention is that none of these scenarios and FGrOW do not take into account irregular non-tree competition. We were not able to address that with the RLP data. And then pre-commercial thinning. This slide outlines an illustrative pre-commercial thinning scenario, results of which are described in the following slides. And the scenario may not make a lot of sense, but I wanted to make sure we had some high densities without thinning. So drag scarification, planting 1,600 trees per hectare, no weeding, and then thinning at a stand age of 13 years, and with target densities that's targeted for the end of the regeneration period of 1,600 trees per hectare, 5,000 no thin. Note that the target density of 5,000 is infeasible where ingress potential is low on the right hand side there, because you didn't have 5,000 trees to start with. And notice also in this scenario the high densities without thinning on sites with modal or high ingress potential. Densities getting up in the modal to around 10,000 and well above that in the sites with high ingress potential. One of the expected effects of thinning, particularly a low thinning, and this is at the end of the regeneration periods, 5 years after thinning. Thinning increases the mean diameter breast height, and note that that increase is related to the pre-thinning density. The higher the pre-thinning density, the more the increase, and it's inversely related to the post-thinning density. But we have to be careful here, because this increase in diameter at this stage of the rotation is attributable in part to removal of the smaller trees through the low thinning, and in part to growth over the 5 years or so that have happened in this scenario following thinning. And of course, the thing about thinning is that you can drastically reduce the basal area, especially at the heavier thinning weights. And in this scenario, the reduction in basal area is not compensated by growth 5 years following thinning in the 1,600 target. See those low red bars in the front. Compare that to the thinning to the 5,000 target, where we see that at least on the modal ingress potential site, the loss in basal area has already been compensated by growth. And projected MAI, thinning to 5,000 to the 5,000 target increases MAI in high density stands particularly. Thinning to the 5,000 target is preferable to the 1,600 target. There certainly is you have to be careful once you start looking at heavier thinnings. Now we have a complication. Because of concern over reduction in growth and yield caused by the western gold rust, the regeneration standard of Alberta excludes trees girdled by western gold rust in MAI projections. But what this slide illustrates is that this supposedly precautionary measure can actually result in a major increase in the yield forecast, and that's a forecast made with the government's own model, as indicated in this slide, where I show at the results of including, that's at the back, and excluding, that's at the front, western gold rust from the projections. And you'll see this at the high ingress potential, you'll see that precautionary approach of eliminating the trees with, not counting the trees with western gallerus girdling, has actually resulted in a big increase in the projected MAI. And this illustrates the considerable uncertainty about the roles played by pathogens. This slide shows the effect of both weeding and thinning on hardwood competition, but only on sites with high growth potential. And I'm going to run out of time, but just very quickly, thinning without chemical weeding reduces aspen but does not eradicate it, as shown on the left-hand graph. On the right-hand graph, you can see thinning with no prior weeding increases MAI, but chemical weeding, basically, the bottom line is that chemical weeding is essential to meet the site potential. And one thing that I think we can all agree on is that thinning reduces the age of MAI culmination, and or at least what we can agree on is that it can be used to reduce projected rotation length. In this scenario, it reduces the age of MAI culmination dramatically at high ingress potentials. And something that I haven't investigated, and I invite you to do so, and you can certainly try it with FGrOW, the effect may be bigger for rotations that are based on minimum tree size. If you're considering, for example, short rotations to try and fill a medium-term gap in your timber supply resulting from MPB or something. So to summarize, pre-commercial thinning shortens the rotation length, increases projected MAI on sites with high densities. Risks and uncertainties include over-thinning. It's certainly not as effective as chemical weeding for hardwood control. We really need to get a better handle on the role of pathogens. And I should mention that the growth model, that is GYPSY, that was used for projecting these effects throughout the rotation, is not based on data which has actually included pre-commercial thinnings. And that brings me to one of the things that Brian asked me to do today, and I've almost left time for, which is make recommendations for the design for ongoing monitoring of the Regenerated Lodgepole Pine trial. And the rationale for this is along the lines you see noted here, that forecasts made by FGrOW for the regeneration phase of the rotation are based on responses to actual reforestation treatments under experimentally controlled conditions. That's the RLP trial. But projections for the growth phase are made by GYPSY from species composition, top height, stocking, and density that results from the prior reforestation treatments. And these projections are picked up and made by GYPSY at age 18 years. And GYPSY and all other growth models used in Alberta are based on either fire origin stand or post-harvest stands without control of reforestation treatments. The assumption is that from the end of the regeneration phase and after reforestation treatments are completed, stand dynamics in the managed stands will reflect those observed within the range of natural stand conditions modeled by GYPSY. This is not an entirely unreasonable assumption, and it is the current best estimate available to us, but it's certainly indefensible if it's not monitored and verified. Which brings me to the objectives for ongoing monitoring of the RLP trial. Conduct sufficient and suitable remeasurements to verify predicted effects of reforestation treatments, adjust measurement procedures and schedules for this purpose, and that's recognizing that the procedures we adopted for the regeneration phase are not all suitable or necessary for the growth phase. Comply with provincial standards for measuring permanent sample plots, and within those constraints, minimize costs. The design and measurements up until now in the RLP trial have been focused on requirements for assessment and modeling for assessing and modeling regeneration. So just by way of example, note here, we've got 16 within each measurement plot, 1,000 meters. We've got 16 seedling and sapling subplots. And we spent a lot of time measuring seedlings and saplings. We are now primarily interested in monitoring tree growth and volume accumulation over the growth phase of the rotation. And the modified design that I'm showing here for the early growth phase, that's for like the next 10 years at least, this relies largely on the existing plot layout and demarcation with a reduction in the measurement plot size. We're knocking the measurement plot down from 1,000 meters to 500 meters, and done in such a way that it will require minimum redemarcation. That is, you basically just have to add a couple of extra boundary posts. And nothing changes on the left-hand side of the diagram. The main changes are what you see on the right with the reduced measurement plot, and we're talking about now only 4 regeneration subplots and 8 sapling subplots, as distinct from 16 previously. So I'll just quickly highlight what I'm suggesting here as the for ongoing monitoring. 500-meter tree plot, 5-centimeter tree tagging limit, measurements consistent with provincial standards, subsampling of height measurement, which has been a major expense in the past, and we maintain existing buffers and corner posts, etc. And in the revised tree plot, the smaller tree plot, we maintain existing and new tree tagging. I would expect this design to result in adequate but not excessive numbers of trees being measured during the early part of the growth phase, with the flexibility to return to larger plots later on. If, for example, later in the rotation, we see stand densities reduced by thinning. And so the next step of this is for members of the Foothills Pine project team to review this and to assess costs. And finally, a couple of additional suggestions. My first one is based on what I believe to be an obvious observation, and that is that we have an insufficient understanding of mortality and health factors during the regeneration phase, as illustrated by the example I described for Western gold rust. And we have done some of this already for armillaria, for example, and which is the example shown on the map on the right. We already have data that could be used for similar assessments for pathogens like Western gold rust, and this might provide an ideal opportunity for university graduate research in that we already have data and it could be done within a relatively short period of time. In any event, it needs to be done to make sure, or in my view, it needs to be done in order to make sure that management and regulatory interventions are fit for purpose and appropriate from maintaining forest health. The second suggestion, and this is my final suggestion, which I have already made in my previous webinar, so this is really my last opportunity to sell it. I have in the last 2 webinars, in this webinar and the last one, pointed out major uncertainty arising from apparent discrepancies between experimental and operational treatments, particularly in relation to herbicide application. And I'm not alone in this regard. Other presenters at other seminars pointed out similar circumstances. And these discrepancies have major implications for cost, for yield, and for credibility. I don't think they can be, well, I think it's important to understand that they cannot be properly evaluated without some level of control. In other words, monitoring treated areas side by side with untreated areas. This is expensive and may be best done cooperatively. And that's why I see development of a shared control strategy for monitoring effects of operational treatment as something that both government and industry really should support being done by an agency like FGrOW. So I hope you'll at least consider these suggestions, and I'll leave you with that. And thank you, and thanks to the companies and the people listed here, plus a lot of unnamed people that I've had the pleasure of working with on the RLP project over the last 20 years. Thank you.